In our systems, we have many resources, and usually associated with these resources, we have queues. And we can have more than one process in the queue waiting for using that resource. Now, in case that we have more than one process, deciding which process will use the resource next, is done by a scheduling algorithm. Usually related to resources and their queues, we also have schedulers, which are processes of the operating system. In our examples, we're going to consider that our resource is the CPU and that the queue is the ready queue, and our scheduler is the CPU scheduler or the short-term scheduler, or sometimes is named the timer. There are different criteria to decide what scheduling algorithm to use for a specific resource. It might depend on the type of the process. We have CPU-bound processes, which are processes that are doing a lot of arithmetic and logical operations, and they have a large CPU burst. We might have IO-bound processes, which are processes that they mostly do listings and IO operations. And in that case, they have short CPU burst. Or we can consider that we have interactive processes, that they interact a lot with the user. Based on these characteristics, usually the interactive processes, they have the highest priority. They are followed by the IO-bound processes and then by the CPU-bound processes. Another criteria to pick a specific scheduling algorithms is based on different time parameters. The waiting time, which is the amount of time that the process spends waiting in the ready queue to use the CPU, the turnaround time, or the response time. We want to minimize these times, and we don't look just at one process at a given time, but we have to look at all the processes, the entire system. So usually we want the average waiting time to be minimal, or the average turnaround time to be minimal, or the average response time. There are two main types of scheduling algorithms. Non-preemptive, and we're gonna go over first come, first serve, the shortest job first, or we can also have non-preemptive priority scheduling algorithms. The other category are the preemptive scheduling algorithms. In a non-preemptive scheduling algorithm, once the process is scheduled, it's allowed to finish its CPU burst. So it's going to execute its CPU burst, and at the end it's going to release the CPU on its own and maybe wait for another resource or event. In a preemptive scheduling algorithm, while the process is executing, it's possible that the operating system, the scheduler, to decide to preempt that process. The process is still in the middle of its CPU burst, so the next step will be to put the process back into the ready queue, and the process will wait to be scheduled again such that it can finish its CPU burst. We're gonna go over Gantt diagrams that they show the use of the CPU based on, on time. And we're gonna use this table. This table will be used for all the Gantt diagram, for all the scheduling algorithms that we're gonna cover. We have 5 processes. The arrival time represents the arrival time in the ready queue, so at what time the process arrived in the ready queue. We're going to go by units of time. So 0, 2, 4, 6 is not necessarily a second or milliseconds or 10 seconds. We just consider to be units of time. Usually these units of time are order of 100 . Okay, so we have, this is the time axis, and here we have the times when our processes arrived. Process 1 arrived at moment 0, process 2 at moment 2, and so on. We're going to start with the first come first serve, which is a very easy and straightforward scheduling algorithm that says that if we have more than one process in the ready queue, the first process in the ready queue will be scheduled. So in our case, let's start at moment 0. We have process 1 in the ready queue. At moment, we consider that at moment 0, P1 it's already there. So P1 will be scheduled. It has a CPU burst of 3 units, so it's going to execute from 1 to 3. At moment 3 in the ready queue, we have just process 2. Process 2 is going to be scheduled and is going to execute for 6 units from 3 to 9. At moment 9, we have in the ready queue three processes that are 3, 4, and 5. So this is when we start using the scheduling algorithm. In front of the queue, it's process 3. Process 3 arrived first. So process 3 will be scheduled and it executes for 4 units from 9 to 13. Next, it will be process 4. Process 4 has a CPU burst of 5, so it's going to go from 13 to 19, and the last one is process 5. Each scheduling algorithm has its advantages and disadvantages. When it comes to first come, first serve, we can see that it's very easy to implement. We don't need to keep track of any specific times. It's just a queue implementation. When it comes to disadvantages, the same as waiting online, if there are very large processes in front of the queue, then everybody else that is behind them will have to wait. So in the end, we're gonna have a poor average waiting time and a poor average turnaround time. The next non-preemptive scheduling algorithm is the shortest job first. The policy is that the shortest process in the queue will be scheduled. If we have, that means the process that has the shortest CPU burst. If we have more than one process with the shortest CPU burst, then we're gonna pick the one that arrived the earliest. So it's before we have the time and we have the arrival times with our processes. At moment 0, we consider that process 1 it's already in the ready queue. There is no other process. Process 1 will execute from 0 to 3. At moment 3, we are done with process 1. In the ready queue, there is only process 2. So process 2 will be scheduled, will execute from 3 to 9. And then process 2 is done as well. At moment 9, in the ready queue, we have 3 processes. Process 3 arrive at 4, 4 at 6, and 5 at 8. We're gonna pick the process with the shortest CPU burst. In our case, that process is process 5 with a CPU burst of 2. So process 5 executes from 9 to 11. Next, we have process 3 with a CPU burst of 4 from 11 to 15. And the last process is process 4 with a CPU burst of 5. This algorithm gives the optimal average waiting time among all the non-preemptive scheduling algorithms. So this is in a way an advantage of this algorithm. A disadvantage is that it's very hard to be used for the CPU, for CPU scheduling, because it's hard to know in advance how long the CPU burst of a process will be. Another thing is that the shortest job first will starve larger processes. It gives priority to short processes, and if we consider the real situation where processes all keep coming in the ready queue, we always can have large processes that will not have the chance to be scheduled due to shorter processes that are in the ready queue. Priority scheduling algorithms. Priority scheduling algorithms can be preemptive or non-preemptive. And sometimes we need to know the relation between priority number and the priority of a process. And that depends on the environment or the language that it's used, programming language is used. For example, when it comes to Java threads, low priority number means low priority. In Java, the threads have priority between 1 and 10. 1 is the mean, 5 is the default priority with which a thread is created, and 10 is the largest priority. In Unix, the priority number, a lower priority number, means higher priority. There are different parameters that are used in computing the priority of a process. Some processes can even have negative priorities. When it comes to priority scheduling algorithms, once a process gets a priority based on its priority number, the general rule is that the next process to be scheduled is the process with the highest priority. If we have more than one process with the highest priority, we should pick